Hey, I'm Julia. I'm a first-year university student here at the University of Waterloo, and I'm studying nanoengineering. And recently I underwent a huge research shift. For the past year and a half or so, I've been researching and building in water purification and clean energy, specifically with solar energy via plants and algae. And now I've switched to public transit with high-speed trains, and I've been working specifically to make the motors for these high-speed trains the most efficient, sustainable, and cheap as possible. And these motors for these high-speed trains are called LIMs, or linear induction motors, and they basically levitate, so to speak, which allows them to travel at these incredibly high speeds. And to do that, they use some pretty interesting math. And alternating current just means that the electric current is alternating in its direction and magnitude, so it's consistently changing there. And the three phases are helpful because they minimize vibrations, which is really important for improving overall efficiency in motors. And it can do this because three phases actually produce a consistent power output in a way that one and two phases just can't. And it's also pretty economically feasible compared to other options, which is great, but more about the three phases later. The alternating current actually produces an alternating magnetic field. And this idea is named after a guy named Ampere. So it's called Ampere's law, and it basically just says that a changing electric current, which is what's happening inside the coil, is going to produce a changing magnetic field, which is what's happening around the coil in the blue. And this magnetic field is important because it actually travels, or if you want to be more correct, propagates throughout the motor, and it actually helps to produce this, the forward propulsion of the motor in the first place. So that is really important. Changing magnetic fields actually produce changing electric fields. So it's basically the opposite of what happened in the beginning. And now these changing electric fields are induced in the top part on the secondary, and these are going to be rotating circular like that. And this actually happens all over again with these eddy currents because these eddy currents are alternating also, they create their own changing magnetic field too. And this new changing magnetic field is opposing the original magnetic field. So the original magnetic field from the coils, everything from there is completely opposite in this new formed magnetic field. And the interaction between this newly formed magnetic field and the original magnetic field from the coils is what actually creates the linear motion in the first place. And this idea was named after a guy named Lenz, so it's Lenz's law. And this is a bit different than Ampere's law, which was stated in the beginning, because this is happening inside an already formed magnetic field. So you have a second magnetic field that's forming inside an already formed one. So then this newly formed one has to be opposing to that. And this opposing phenomenon is what creates levitation, and it creates the propulsion that we see before. And on top of this, because there are so many coils, and because each of these coils have their own magnetic fields in them, it looks like it produces a moving magnetic field that moves along with the motor. And this is actually what's happening. It's a traveling magnetic field, and this is what pushes the secondary across and allows it to move linearly. So three-phase is by far the most commonly used phase today, and it uses three different coils, and each of these coils are separated by 120 degrees equally. And this arrangement is so common because it actually produces a consistent power output in a way that one phase or two phases can't. And this is a bit more obvious to see in graphs form.
So electricity in LIMS uses alternating current, and alternating current we know changes in direction and magnitude, and so they're described in waves like this that go up and down and up and down, and they start at this 0 point. All of them start in a few different places, and they end at 360 degrees, which is one full unit of movement. And in rotary motors, this is one rotation, but in linear motors, it's a bit different because linear motors, since they move linearly, their one full unit of movement is the distance that a motor travels based on one pulse of thrust. And here, each of these three phases are separated by 120 degrees, and here it's put in radians because it's more specific and it's more accurate, but 120 degrees is 2 pi by 3. And so this blue one here is the default one. It's at 0, so it has no changes in its equations, but this one is separated by 120 degrees to the left. It's backwards here. It's supposed to be like that. And then the black one is separated by 120 degrees to the right. And when you add all of these up, it makes a horizontal line. I'll show you here. See, it makes a horizontal line, which means a consistent power output. And this is an interesting phenomenon that doesn't only happen with three phases, but it happens with all multiple threes that can do it, or phases. And this is really important because when you have this consistent power output, it hugely minimizes how many vibrations you get in your motors, which is really important for creating the most efficiency possible.
So, a common question I've asked myself hundreds of times throughout this research process is why three? Well, if we can use three, why can't we use 6, 9, or 12? Wouldn't we get even more power? Well, I found after a lot of research that after a point, it just becomes impractical to use higher phases because you would need to use 6, 9, or 12 separate coils, and each of those coils need their own electricity source and their own circuits to get to the motor. So it's a lot of extra hardware and a lot of extra costs for really not that much power output. This is because after 6, the math just doesn't work well anymore. To get to 6 phases, you would double the phases of 3, so you'd have 2 3 phases in one, and this way you'd get nearly double the power. But it doesn't work the same way for if you double 6. If you double 6 phases, you get 12, and this is not even 4 times the power output you get from 3 phases. And that's the same with 12. You can't double 12 anymore to 24 and get a higher power output. It just doesn't follow through. It's a diminishing return. So now it doesn't make sense to go to higher phases if not even the power output is doubling. Each time you double a whole phase with all its wiring components and that come with all those phases.